Okay, hi. All right, so I wanted to go through the homework paper this week, which is this, let's see, wait, I have to share desktop. There, that's good. And hide that. Just this paper by a Japanese group. So they're at so Institute of Science in Tokyo, and I guess they're both at the Institute of Science in Tokyo. No, wait, and then the other's in Department of Energy, Nagoya University. So, so they're interested in this problem of depolymerizing polymers. So the problem of microplastics and plastics waste and nanoplastics. The idea is that you could kind of unzip the polymers into monomers, and then you could reuse the monomers to make another polymer. And generally that's done with PET. I should have put a link in here to PET. That's the polymer for water bottles. Let's see. This is no wiki page for that. T depolymerize PET hydrolysis that can depolymerize, break apart. So that's basically water, polyethylene terephthalate, so it makes terephthalic acid. And this company's Eastman Chemical is doing that. Probably a web page. Eastman updates for massive PET recycling plants in Tennessee, kind of east of Oak Ridge or Knoxville. So on the Kingsport, Tennessee, some of the Tennessee River. So anyway, some people work there, and they've been doing that for quite some time, this depolymerization process, and they're trying to upscale it a little bit. The problems always come down to economics. Like, is it economically viable to do that? So anyway, so this paper is looking at that for something like PMMA, like plexiglass polymer, which is a free radical polymer. So let's see. So generally, free radicals polymerization are going to be not sure if that's a picture of it. So you take a polymer like ethylene. So you have double bonds. So it's carbon like that, right? So and then you attack it with like AIBN as a free radical initiator that ends up with two nitrogens with free radicals on them. And they attack that, and then that'll polymerize into carbon-carbon, and then another double bond with or carbon-carbon with a free radical at the end of it. And that can go attack another ethylene unit. And then the polymerization goes, that's a chain polymerization. So that's going to give a polydispersity index of, at best, you can get MW over MN equals 2, and generally higher than that. Right, so like polyethylene is going to be 16. So all the vinyl polymers you can make that way. So you have like styrene, polyvinyl alcohol. Polypropylene is a little bit different because it's got a resonance structure like that, which prevents it from this kind of free radical polymerization. So you have to polymerize that with a cyclonatic catalyst or with a metallocene. So different kinds of specific site catalysts where the catalyst kind of holds with their hand the double bond while it polymerizes, so it can't do this resonant dance where the double bond flips back and forth. But PMMA is one, so it's got a methyl group, and then it's got an acrylate group over here, if something like that. So methacrylate would be a methyl group here, and he's using benzacrylate, so it's got an aromatic group over here, like a benzene ring. Right, and then you polymerize that in the same way, it opens up the bond. So that's a typical free radical polymerization. So around 2000, 1995 to 2000, they invented a new kind of polymerization for this, which is called was called living free radical polymerization. So let's see, I should mention that there's other kinds of polymerization that you can do with vinyl groups, some vinyl groups. You can do an anionic polymerization. So if you have a polymer group like styrene, where this stabilizes the double bond here, the aromatic ring, because it pulls electrons out, then you can get a stable anion form here. And then the anion can propagate like the free radical did and attack other double bonds with a stabilized group on the side. Then you can get from this kind of polymer. So this kind of polymerization, it ends, the free radical polymerization ends when you have a double bond can combine with another double bond, then that thing just terminates the reaction. Or the double bond, the free radical can go attack and pull a hydrogen off and make a branch site. So disproportionation of the chain. Right. So basically there's a couple mechanisms for ending a free radical reaction. That's why it ends up with a polydisperse molecular weight distribution. We plot probability of number versus molecular weight, then you get some kind of broad hump to it. When you do anionic, these things don't exist. So you don't have there's no termination. So the reaction just goes until you run out of monomer. And if you start it all at once, you end up with monodisperse. And the probability versus X, you just get a spike, single number. So MW over MN would be something like 1 or 1.02. And the other one's going to be 2. Right. So there's some advantages to that. One advantage of this anionic is that you can run it on polystyrene and then you run out of styrene monomer. And then you can put in butadiene. So you can make a styrene, butadiene, styrene block copolymer. So like S and B, then S. So styrene makes a glass at room temperature, butadiene's liquid, so you have a thermoplastic elastomer. You can extrude it and it'll make a rubber. And if you heat it up, the styrene goes through glass transition, then you can extrude it. Or you can make tires from that. You can go in and the butadiene's unsaturated, like these will polymerize and they get the double bond in the middle. So basically it's still got unsaturated bonds that can be attacked by another free radical or by sulfur to cross-link it into a rubber. So usually the SBR for tires, they put sulfur in or some thiol to bond it together. So sulfur will also attack the double bond. Right. So anyway, and there's also cationic. That would be for groups that have stabilizing groups for a cation, which would be like polyvinyl methyl ether. There's an example where the cation is stabilized by the side group. Both of these have to be done in dry conditions, so no water, no oxygen. Free radicals a little bit accepting to different conditions. So at some point, chemists came up with a way to make this reaction work like those reactions. That would be a living, what we call a living free radical reaction. Right. So that's this thing. So there's a wiki page. So basically, within the family, so the idea of the living free radical polymerization, and I'm not an expert, by the way, but so by no means a chemist, but basically the idea is originally you have some ionic group, like a metal, that's going to take the free radical and protect it so it can't proceed. So you have your chains propagating, they have a free radical at the end. This metal coupling agent, so it's a chain transfer agent, CTA. It's going to take the free radical and scavenge it and then leave a stable group here that doesn't polymerize. So if the free radicals, the population of free radicals in the system is so low the two free radicals can't find each other to terminate the reaction. So if you can reduce the number of free radicals in the system, then you never get a termination. Then it'll act just like an anionic polymerization, and you can get a MW over MN of about 1.1, maybe sometimes 1, right? And also you can do, if you do this the right way, you can also get block copolymers from this route. So you can take the whole slew of polystyrene, PMMA, polyvinyl alcohol, any kind of vinyl polymer, and you can go this route and make monodisperse instead of polydisperse. So this is thought of as like a big deal when they sorted this out. And there's a lot of patents on this polymerization. And people have made like companies to do this. I think industrially, I'm not sure that it's used that much, but in research, it's used a lot, right? So anyway, of the living polymerizations, of the types of these free radical, living free radical polymerizations, there's several categories in here. So you can kind of look at, let's see. Is this the one that's got free radical polymerization? One of these has a list of these. Yeah, oh, here, this is it. So stable free radical was the first one that was invented. And then ATRP was the second one. That's one where a metal ion's going to pick it up. And this Polish guy at Carnegie Mellon became like famous for this. He had a huge group and basically a building practically to do this work, 95 to 2000, right? So basically this is 25 years ago, but basically there's a huge thing going on. Then later on, I think it's the Australians and someone else invented this raft polymerization, which doesn't have the metal ion anymore. It's got a more stable chain transfer agent that's going to hold on to the free radicals, so you don't have a high population of free radicals, so they can't combine to terminate. And they involve these thiol groups, the double bond S, right? And that's a resonant structure like a double bond O is, so that double bond can flip to the other S. Right, so this is a stabilized system, so that the sulfurs, the thiols can stabilize a free radical and trap it, just like the metal ion does for ATRP. So it's the same idea, it's just like a different system. It turns out this is like an improved system, this raft polymerization. So that's what they're using. And it also turns out that for certain polymers like PMMA and this PBZMA that they're using in this paper, that this thing can depolymerize if you raise it to the right temperature. There's an equilibrium between polymerization and depolymerization, and there's no termination in it either way. So you can take a polymer, make it by raft polymerization, ends up with a thiol N group, and then you can make a part from it. So you can make a plexiglass window, then smash the window, and then put it into a solvent. I think he puts some more of this thiol chain transfer agent in, then heat it up to 120 and it'll depolymerize. So you can take your broken window, make it back into monomer, ship that to Tennessee, and then they'll make another window with it. That's a brand new window, no different than the window that you started with. Right? There's no, right? So the idea is like you can get pure monomer from this process. So it's good. Sounds like an interesting idea. I mean, all these things, and there's other ways that people have dreamed up how to do this trapping the free radical so they can't recombine because there's not high enough density of free radicals to recombine to terminate the reaction. Anyway, it's an important enough thing that everybody does this, like everyone is doing this raft. The other thing is that this is very, very insensitive to the conditions. So you can run this in your bathtub, right? Whereas the anionic polymerization, you have to have some seriously special oxygen and water-free environment to run it. These things are basically like you can do this in your sink. It's not going to. So basically, they invented a way to make your normal Joe's monodisperse polymer. So in that sense, it's kind of interesting. This is the thiol that they're using in this group, and this one's kind of tuned for this depolymerization. The cyano-2-propyl benzodithionate. So this is called a carbothiol. So carboxyl thiol, they call it. So carboxyl would be like double bond O. Carboxyl thiol is the same thing with an S here. And S again has this thing that will attack double bonds. And then if you look millipore sigma. Then they kind of give an overview of the different kinds of chain transfer agents that you can use for this process. So this is another one of these like seemingly complicated, but basically grunt chemistry. It's like the condensation reactions to make PDMS. This is like basically any idiot can do this as long as you buy the right chain transfer agent to go with your monomer. So the monomer is listed up here, chain transfer agent, and the more pluses, the better. So if you're going to do polymethylmethacrylate, you probably use this chain transfer agent, for instance, or you could pick with this table, and these guys will sell it to you. The chain transfer agent, which is like kind of like a catalyst here. Anyway, so that's said, that's kind of a mouthful, but I think the point of this homework is to introduce you to this chemistry in a sense, even though it's a physics class. And also we're talking about rates of gyration and the Debye function for polymer coils. So for scattering, and he's also using the Zim plot, which he calls the Berry plot here. So basically it's got kind of 3 or 4 things that are interesting in it. Let me go to the wider view picture of this paper inside the PDF. So let's see. So what do I have here? All right. So yeah, he goes about his first he polymerizes with this raft process. He ends up with a thiol group at the end, and then he's going to put the chain transfer agent back into a capillary, stick it into an X-ray beam, and watch how the structure degrades. Right, and he's trying to basically distinguish between 2 kinds of degradation. One would be what he calls unzipping, which is as he depolymerizes it just the way he polymerized it. He takes off monomer, monomer, monomer. And the other option would be random scission, which would be like take a pair of scissors and chop it wherever. Right, so those should lead to 2 different populations of chains that come out, and he's got the calculation for the unzipping, which would be the end unzipping, like pulling off the monomer by monomer. He calculates it here, and then he calculates in the supplemental what the random one would be. And I'm not really that up on. Anyway, these are just population balance equations. See the change in chain concentration of molecular weight X, or X number of monomers, is if you have I and then the dissociation constant for I, and then this thing is the termination of the process, like 2 free radicals die. So 2 free radicals of X die, then that has to deduct from it. And then every time you have an I degrades, then you get an X from it or something like that. So basically these are just like the, what's it called? The Stalinowski equation is like this for particle growth. And this is just the same thing for polymerization, like change in rate of change of one. So you have a population of X's, 10 or 15 CX's of different molecular weights. And then this is a change of that particular one, the time, and he only allows degradation. He doesn't have a growth one. So usually they have degradation and addition. So it'd be 2 terms, it's KD and KA. Here he just uses degradation. He says it's a one way. It's only degrading at 120. So anyway, so this is a random scission process, and his in-group scission thing has it just going to produce 1 monomer, P1, instead of some splitting into 2 polymers. And then he ends up with an equation that has a different result in terms of the concentrations. And then he follows the thing we went through in class to get this Z average, quote unquote, Z average radius gyration. So he takes the mass of the chain squared. That's where he gets the Z average times RG squared, and then his populations of X, and then normalize by that thing. And that gives basically a Z average for the thing, if you look at it that way. Right, so we ended up like, if you convert X to RG, then you end up with the eighth moment over the 6th moment, but here he ends up with the 3rd moment over the 2nd moment, which would be the Z molecular weight, Z raised to gyration. So depending on how you look at it, it's still a really high moment of the distribution. So you expect that you're only seeing the largest chains from this. Right, so that what we said, like race of gyration is not a good measure of size if you have a polydispersed population, because you're only seeing the large things. This is true of this equation too. So if you only see the large things in a degradation process, you don't see the small things that you're spitting off. So you'd expect that the rate of gyration doesn't change, and it doesn't change. It doesn't change at all, right? I mean, he says it's a little lip. Basically, it doesn't change at all. Like over his entire process, 100 minutes or up to 100 minutes process of degrading, doesn't change at all. And then from the zero intercept of the scattering, so I0, you get the molecular weight of the chains, the weight average molecular weight. So that's pretty clean. And he gets that from a Zim plot, which he calls a Berry plot, which is somewhere in here. I guess it's in the supplemental over here. He's got the Berry plot. This is his Berry plot, which is really a Zim plot. So he does different concentrations and extrapolates to zero concentration. The slope gives you RG, the intercept gives you kind of the molecular weight, right? So that's basically the Zim plot. So anyway, so you can get the molecular weight pretty good. From the slope, which looks pretty clean, he should be able to get the rate of gyration. Okay, and he says the rate of gyration is something really small, 3 nanometers, the 30 angstrom rate of gyration. So that's suspect immediately, okay, because so basically, if you take 2 pi over 3 nanometers, you get 2 inverse nanometers, right? So you look at his plot. So 2 inverse nanometer is not on his scale. So 2 pi over q gives you the size. 2 pi over rg gives you the q. And if you take 2 pi over the number he has, he's not measuring there. All right, so that's number one. And also if you figure out, well, here's the knee, so that's about at 0.5. So 0.5, 2 pi over 0.5 would give you 12.4 nanometers, right? So 12.4 nanometers is a lot bigger than 3 nanometers. So something screwy about this. This should be a good way to get the molecular weight. He's going up to Q of 1. So this plot, even though it's Q squared, 1 is still 1. So he's going up to here in that plot. And the RG, this uses a Guernier approximation. So it's like the knee part and takes a dive. That's really happening around 5.5. So there's part of the problem is he isn't in the right Q range to get the RG. Like the RG would be over to the left significantly on that. Anyway, you can just look at this and know that's about 10 nanometers size things, 100 angstrom. It's not 3, right? So anyway, so that's kind of a major problem. That's major problem number one. And then major problem number two is that, all right, so he's going to fit his data to the Debye function. So he's doing a Zim plot to get the RG there, but he also does this Debye function. Then he says, well, there's a problem with the Debye function because it's power 2. So if you say this slope out here should be -2, so it's 2-dimensional. So log plot should be a -2 slope. Then if you go q squared RG squared, or if you go q squared I, that removes the 2. That should make this part totally flat if that's actually 2. When he does that, it's not totally flat. It tails down, right? So why does it tail down? That's because the dimension isn't 2. And if the slope out here, right? So in order for it to be a lower intensity than what you expect, then this thing has to be steeper than 2, which means that it's branched, right? In other words, he's depolymerizing and he's making branched structures in the process that goes down. So that's incompatible with this model, kind of with this cartoon here. Like there's no branch in here, right? So that's a little bit of a problem. So how is he going to deal with that? Well, so he says like, oh, at high Q, you see the chain diameter, as if you're going to, so this is his model. Let's see, where's my thing here? Here. All right, so his model is that he's got random coil, so df equals 2. When he gets to small size, then he sees like the diameter of the chain, like this thing. But he never sees the persistence, which should be a -1. So he should get that thing -2, and then it should go -1. It should go up. And then maybe if you could, no one's ever seen this, but it should go down like a guinea, then maybe something else, like a -4 over here. So he takes a function e to the minus q squared rg squared over 3 and says he's just going to tag that onto this thing. So he'll get a curve like this, -2, and then boom, down, right? So that seems screwy. That's totally screwy. You should see -1. You shouldn't see that thing. So that's totally messed up. And the other problem with this is that the size he gets for RG here is 1 nanometer, 10 angstrom. And if you figure out what 1 nanometer is, so 2 pi is 6.2 divided by 1 is 6.2. So where that knee part is, so this is 1, 2, so 3, 4, 5, 6. It's like over here, way off of, he's not anywhere near measuring that. So on the region where he is, all he sees is the all he would see. So he doesn't do the -1, so he just has -2, and then he's got like a flat number coming in that he just adds to that. So he's just putting in like a background that makes it's meaningless, right? It's totally screwed up. Plus the RG he has here is way over there. So the whole thing is like, how could he possibly fit it? I mean, it isn't possible with the numbers that he gives. So, but yet he shows this Gaussian chain curve that matches the data. It's like totally messed up. Right? The fits are insane. I mean, totally insane. These functions are just, there's no reason you would have this. They aren't Gaussian, so none of this stuff makes any sense. And somehow he just shows it here like it fits the curves. So it's possible to fit the curve of the function that's totally meaningless. And then he says, like, he has this one chain that hasn't degraded yet, and then he has these small chains that are floating around that have a size. So these chains have an RG of 1.2 angstrom, the small chains, and then the diameter of those is still 1. So it's not a chain if it's got 1.2 and then it goes to 1 for the diameter of it. It's actually a brick, right? So it isn't anything like a chain. So the functions here are like way off the deep end of the pool. Like he's gone underwater and he's drowning with his stuff. Right. So it's pretty messed up. So it's short, actually it's a short paper, so it's nice. It's like 3 pages. It deals with this RAF stuff. The molecular weight dependence of this, that's probably good. You know, the zero, so that he sees this nice trend where it drops down. Then he fits that with his unzipping model and he says, yeah, it's unzipping. But he ignores the fact that his original data shows that the chains are branched, right? So they're branched to start with, they're branched to end with. It's a messed up system to start with. And it doesn't show any persistence. There's a couple of problems with it like that. Anyway, so that's kind of where I am with this. So he says, let's see, page, so this, because it isn't printed yet, it doesn't have page numbers. It's got page A, B, C, because I don't know what the pages will be once it gets in the journal. This is a proof. This is a preprint, they call it. But over here, he says, divided by optical constant C, sex profile clearly exhibits a monotonical decrease in I by C over time, evidencing the decrease in the molecular weight. That's true. Then as IQ generally follows, meanwhile, the slope in the low Q region appears to remain unchanged. So what he's talking about is like over here, like this. So the slope there isn't the slope. It's like less than power 1. Like if you took 1 decade and 1, that would be power 1, right? And this is less than 1. That means it's not a slope. Like it's not, no object has a dimension less than 1 in 3D space, in any space, right? So there's no possibility that slope has to do with the structure that he's thinking that it does. Like he mentions that it does. I mean, there's a bunch of problems with this. He mentions that this slope has some meaning other than it's just the rate part of the Guinier function. And then he's talking about the size of the chains, but he's measuring it way out here where he's off the scale. And he's ignoring this thing, which is like 12 nanometers, right? So right, there's significant problems with the scattering analysis in this. So that's one part. And then the bottom, he says high Q increase. So he says something about he says to generate further, let's see, he says something high Q here, so you can find it. High Q. High Q region. No. For exponent to, so it's anyway, it's not the same B page at the bottom here. There's an X-ray, furthermore, fidelity, sex, conduction. Remarkably, the high Q scattering the Kratky plot increases over time. So that's this thing. This is kind of a Kratky plot. It's Q squared times I. So that would be a Kratky plot. So he's trying to remove the power 2 by multiplying I by Q squared. And then you plot it against Q. It's a normalized Q, QRG. Right. So I don't know why one is like way over here. Because one, if his size is actually 3 nanometers, it would be way out here somewhere. So something screwy about the QRG here also. It looks like he's using a different RG for this, but anyway, so over time, this drops down. So it's initially steeper, means more branched, and then becomes less branched as he goes to his higher depolymerization. I don't know what that means exactly, but he doesn't interpret it that way. He interprets it to mean that his Gaussian chain model with RG3 in a cross-sectional diameter, and then in other words, he's using an arbitrary flat background to adjust this thing over time. It's pretty screwed up. Like how he fits these curves to get that to work is messed up, and the whole thing is a little bit messed up in the analysis here. Nicely fitting the Sachs profiles, blah blah blah. So let's see what else. And then he talks about this bimodal thing that I mentioned. It has two Gaussian functions, two Debye functions. And then the Zim analysis, which he calls a Berry plot, should be good and should get a good RG out of it, but he's not in the right Q range to get it. So if he had just done his linear fit like at the lowest possible Q, he might have seen the right RG. I think that's maybe what's going on here. Anyways, that's kind of the story. Overall, it's short. That's good. But it's kind of messed up. In the short distance that they have, they've managed to make a noose and hang themselves from it. I guess it's my interpretation of this. So anyway, so that's that paper. Let's see what the questions are here. Actually didn't time this. So what am I doing on time? Well, I don't actually see the time here, so hopefully it's okay. Let's see. I'm gonna go to my questions though here. So let me blow this up a little bit. That's good. So what is raft polymerization? So I kind of go to the wiki page, it'll kind of tell you raft and ATRP and living free radical polymerization. And then the interesting thing, we have an expert at UC, this guy Neil Ayers in the chemistry department, who's also like some kind of administrative thing now, like super provost of something or other. But basically, this is a 2023 paper, which is in here somewhere. That's not it. Here. This is Neil Ayers, right? So he's our guy, and he teaches the he teaches a polymer chemistry class. So some of you might have taken his class, and I'm pretty sure he'll talk about ATRP and raft polymerization in there. I think it's supposedly like a broad polymer class. Basically, I'm pretty sure he deals with. So he's using raft polymerization, and so the raft is going to use the thiols, but he uses a different thiol. So what he's doing with it is he's making block copolymers with it that are narrow molecular weight distribution. It's kind of what you use it for. And the purpose of those block copolymers is to make acoustic materials by this reactive copolymer surfactant thing. So you don't need to I'm just saying like so AIBN is a free radical initiator, and then benzyl peroxide is another free radical initiator. So these, when you heat those things up, they make nitrogen with this makes nitrogen with a free radical. This makes an oxygen with a free radical. So both of those, you heat them up and they'll make free radicals. Benzoyl peroxide is like a zit ointment material also, you may have heard of. And I think it does that by free radical kills the bacteria or something or other. But so you can eat it or you can use it in a polymerization, or not eat it, but So anyway, down below he talks about his RAF polymerization, and then he's got a chain transfer agent. Let's see, does he say what it is? AIBN's his free radical initiator, and then the chain transfer traps the free radicals. So it's kind of the same thing. It's just showing the flexibility of this. Like you go from this PMMA, which is pretty simple, to something that's really complicated using the same kind of mechanism, And you can see like here he shows like his raft. So because he can stop when he runs out of monomer, the reaction stops, he can add in the other monomers. He can have gray, PDMS, SIO kind of chain. And then he sticks on some alkane thing, and then he puts another PDMS and he puts another alkane. So you can build all kinds of architecture. You can make star things. You can do anything with this. So, oh, this is his chain transfer agent. So he's got this, with raft, it's always going to be a thiol. It's always going to be a carbonyl thiol, like a carbonyl group with an S on it. Right? So, because that'll switch the double bonds around this, so you can store a free radical in it, like forever if it wants. So some kind of rate of exchange of the free radical from the chain to this, and most of the time the free radicals live in this thing. That keeps it so there's not enough free radicals to combine to terminate. That's basically the idea. I think there's some advantages of these thiols, and that you can use different solvents and you can use different monomers. So basically, the raft is more flexible than the ATRP, which is the original Carnegie Mellon process. But it's the same idea. Like find something that can store a free radical most of the time and release it sometimes. So any molecule that would do that, you can use. And the wiki page gives like 6 examples that are popular. Anyway, so I threw this in so that you could just kind of compare. Like you don't need to read anything in detail. Uses small X-ray scattering, and then this polybenzyl methacrylate and paraxylene. He heats it to 120 to get it to depolymerize. He shows the kind of does the molecular weight thing with the Zim plot, and then what he calls a Berry plot, and then playing what moment of the race gyrations came from polydispersed. That's his equation 8. So he calls it a Z average, and then reference. This comes from so there's this June Rowe book, page 170. He goes through that. I showed that in class, and there's also this reference 29, which is here. So I think I didn't open that yet. So it's already open. So this is a tutorial on scattering, and it goes through that Z average thing. So it goes through similar what's in the Rowe book. These guys are at Oak Ridge. So the neutron scattering people, but the same rules apply. I guess Case Western affiliations. There's the Oak Ridge group. Hora moved around. He was at Oak Ridge, and this Way I thought was at Oak Ridge, but maybe not. Anyway, so I guess this is just Case Western, Journal of Applied Physics, and then anyway, so this is just saying like what moment is a race gyration, and I think the point of that is that I talked about molecular weight distributions, and the high order moment doesn't change. It's only because you only see in the absolutely the largest thing. And when you depolymerize, you're making small things. So basically you have a beach and then you throw a hand grenade into it and you break up the sand, but the big boulders are still there. So that's why RG doesn't change in the system. The authors go through a long process of explaining why it doesn't, because of the mechanisms of the degradation. Basically, you don't expect the race gyration to change because it's just looking at the largest things. If they don't break down, then you're not going to see it change. Anyway, so C resolve depolymerization as unzipping compared to random fission. Just explain the two things. Like he shows, just explain the difference between unzipping, and that is how can molecular weight drop while RG remains constant, figure 2C? Well, there's two explanations. There's his explanation and the fact that RG won't change because you only look at the largest things with it. I think that latter explanation is simpler, than his pretty complicated reaction mechanism. And then if you're all right, this is a good question. Like if you're depolymerizing, if you're doing this in a recycling scheme, which one do you want, right? And I guess I don't know which one you want, but basically maybe unzipping is better. I guess if you really get monomer from it, I guess that would be better. So it's kind of hard to tell which one you want. I mean, I think you should think about which one you would want to do. Then figure one shows Sachs results plotted on 3 different plots. He claims that the power law slope at high Q is -2 because he's using the Debye function to fit it, but it isn't -2 because when he does the Kratky plot, so IQ squared, it doesn't go flat. It would go flat if it was -2. So it goes down instead of flat, which means that it's steeper, the steeper slope than -2, which means it's a branched polymer, right? And he doesn't understand that. So, and to make the curve drop below horizontal, you have to have a higher fractal dimension. And if it's going from 2, it has to be that it's a branch chain. I think that's probably the option you have. S6, S7 include the Debye function for Gaussian polymer chain, which is not expected in a good solvent, right? So the chains, if it was a linear chain, unbranched, and you put it into a good solvent, which paraxylene is a good solvent at 120, then you don't expect it to follow the Debye function because it's an expanded coil. It doesn't have a -2 slope to it, which means this function wouldn't work. And then adding in this skinny term at the end doesn't help. Like that doesn't even make any sense. And then it says like what sizes he got for it, which the sizes don't make any sense. And then because they don't match the Q range that he's looking at. So this would be way off the Q range that he has. And then normally what you'd expect at high Q for polymer chain is a persistence regime. So you'd see a -1 slope. So it'd be a lower slope, not a higher slope. So it wouldn't go -2 to steeper, it would go -2 to shallower, right? So he doesn't see that. And that he doesn't go to high enough Q to see it probably. And then comparing this function's exponential term, which have no reference number. So he just made up those functions. He's not catching that from some paper. Like he just threw that together. So so if you compare that, so he gives this function, let's see, this is given in the supplemental. So he gives this function, whatever that is. So he just gives this a q d squared over 16. So where is this 16? This should be, it's going to be as low as q squared rg squared over 3. Right, so where does the 16 come from? So 16, d here is the diameter, right? So the 16 comes from, if I can find this thing, the 16 comes from, like we have the moment of inertia, blah, 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 blah. I'm almost there, not quite, but I should just go there. It's probably out somewhere. RG, out there, moment of inertia. So you have 1/4 r squared. If you put in d, it's d by 2 squared is 4. So 4 by 4 is 16. So that term, that's rg squared is r by 16. So that means for a rod, it's a 16 thing comes from there. That's a rod function. So if you just compare this, if you compare that, so you have, let me write that down. So you have, let's see. Q squared rg squared over 3. And he has exponential q squared d squared over 16, right? So let's see. Here, so he's got that. So you can just say you get about Q squared, and he's got RG squared equals D squared over 16 and 3. Right? So you can kind of get an RG from the D. He reports D equals 1 nanometer. So if you have 1 nanometer here, what's RG? So it's 3/16 square root is RG, right? Whatever that comes to. So he's got, and if you look at that RG value, it's going to be such a small number. Let's see, I'll do it over here. Let's see, all my phones being used. Square root of 3/16. I think it'll just do it for you, maybe 0.4. So 0.4 nanometers, right? So 4 angstrom, and then 2 pi over 0.4 nanometers. So you can do that for, let's see if we'll do that here. Let's see, let's do that in here. 2 times pi divided by like 4/3 or something. Gives you 14. Okay, so he's got a 14 nanometer to the -1. That's the Q that you would see there. And if you go back to his paper, so you'd expect to see a knee at 14. He goes up to 1. So it'd be another order would be 10, and then over here. Right. So it's so far off of his range that it's like you can't measure that with this data. Right. So this term, all it's going to be is a flat number. And it's not, it doesn't do anything to the thing at all. Right. So anyway, it's pretty messed up. Like the whole thing, like if you figure out like how that would look on the curve, it doesn't match up at all. Yet he still is able to get like a line that fits the data somewhere here, like these things. So how that works, it's pretty hard to decipher. Okay, let me finish. So that's kind of what this is getting at, is how does that make any sense? And then however, the unzipping model of a chain becomes highly suspect if the chains are branched. So if they're branched, unzipping becomes pretty complicated, right? So anyway, so it's just kind of like looking at it, like hash through this thing. It's a short paper. Hopefully it's easier than the other ones, because it's just a simple thing they're doing. It's just they've kind of muddled it somewhat, so and look, the way things fine. The rest of it's pretty messed up. So anyway, that's about it for this thing. Hopefully that's okay. You can email me with questions. Hopefully I can answer. We're going to be like running a machine like 24 hours a day for 4 days. So it's hard to tell how coherent I will be. Anyway, so that's about it. So thanks. Sorry I'm not there today. Anyway.